Welcome everybody to the SCG Europe Regional Advisory Committee's webinar series, State of the Energy Industry in Europe. Dr. Adriana Ramirez, Chair of the SCG Europe Regional Advisory Committee, and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short presentation followed by an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the interface and or put your questions in the chat box, and we will get to your questions right away. So today our presenter is Dr. Horst Roeder. He is president of Harbor Dome Consulting in Cologne, Germany. After 32 years as head of the geophysics department of DMT, he nurtured the growth of DMT from a small research group of the German coal mining industry to one of Germany's most important private geophysical contractors. During that time, he was responsible for more than 100 research projects for international, public, and commercial agencies, as well as for the mining and oil and gas industries. He continued significantly to development of 3D seismic methods from 1975 onward. He holds patents on seismic instrumentation and on specific logging instruments. His emphasis has been to integrate geophysical techniques into mining and borehole applications. Horst holds a PhD from Ruhr University in Bochum, Germany, where he is part-time professor. He is member of many professional societies, and he serves on several editorial boards and professional steering groups. Presently, he serves as chief scientist of the German Geothermal Society, as board member of the International Geothermal Association and the Geo Union. Alfred Wagner Stugan. Horst is widely published and wrote a book on in-seam seismics. He received, besides other awards, in 2001, SCG's Special Accommodation Award, and in 2005, EAGE's Konrad Schlumberger Award for taking geophysics beyond its boundaries. Today, we welcome Dr. Horst Roeder. Take it away, Horst.
So, hello. I also want to say hello to all of you, and I'm very thankful that you joined the today webinar, and I excuse myself for the problems we had to start. So the topic is the geophysical exploration for geothermal reservoirs, and of course the exploration is more, but we concentrate today on the geophysical part. I refer mostly to a book which is called Geothermal Exploration, which was written by Harvey, Birdsmore, Möck, and me, and is published by the EIG academic books. And of course, this book contains all type of exploration, and today we talk only about the geophysical part. So the exploration is, of course, embedded in a series of different phases for a geothermal project. So normally, we in the international literature we have 8 phases, and we start normally with a preliminary survey. Then we have the exploration, which normally includes shallow drilling, but that is not accepted by everybody. Then we have the test drilling phase, so these are deeper boreholes going into the reservoir. We have a project review and planning, a field development, a power plant construction, commissioning, and operation. So these are the different parts, and they are of course connected to costs and risk. And if we look at this slide, we can see that the exploration, these are again the 8 phases, and the exploration lowers of course the risk, but the main lowering of the risk is due to the test drilling. But again, the costs are very low for the exploration alone, and then they start with the drilling, which are the main costs, and later on the power plant, of course, is also a costly part. we have worldwide many geothermal installations, and we can, of course, or we need to divide them into groups. Also to talk about the exploration, which may be different for different groups of geothermal sites, and there are many different ways to sort the geothermal sites into different groups. So one is shallow, medium, and deep. Another is low, medium, high temperatures, or low and high enthalpy. Also maybe a hydrothermal and petrothermal, or EGS as a point. So today I want to use the dividing the geothermal sites according to their geological place. And this was introduced by Birdsmore and Möck, and I want to show this in the first part of my presentation, but because later when we talked about the geophysical tools, and we have to talk about which tool is the best, or which group of tools are the best for which geological play. So the main differentiation between the plays is, are they more convection or more conduction? So in the convection, we have a higher permeability in the reservoir, and the heat is transported together with the fluid. So we have a fluid flow system, and the fluid transports the heat. In the conduction dominated systems, we have mainly a conductive heat flow, so independent from the fluid flow. But of course, I wrote for both sides dominated because it's not poor. So we have in convectional systems, of course, also conduction, and also in a little permeability situation for conductive dominated systems, there may be some fluid flow and also transport of energy together with the water or steam. So we subdivide this in many parts. So in the convective, we have the magmatic place, the plutonic place, and the extensional domain. And for the magmatic, we can have an extrusive, so magma coming to the surface, or intrusive, so magma flows below the surface. In plutonic, we have not the magma flow as much, but a present plutonic hot part from which the heat comes, and it can be associated with active volcanismus, or it can be without active volcanismus. The extensional domain is a geological domain where, due to the extension, there is a lot of water flow possibilities, or a high permeability because of the extensional regime. In the conduction-dominated systems, we have intercratonic basins, so big basins in the middle of the tectonic plates, and no relation to the plate boundaries. We have the orogenic belts, which are the plate boundaries, and geothermal systems connected to those. Or we have the crystalline basement, which is in the mainly has a low permeability, but has, of course, a huge volume of heat. So I want to go a little bit more in details about that. So the 1A CV type is the magmatic play with extrusive magma. So the magma coming up is going to the surface, and we have active volcan areas, and on the sides we have acid pools, we have geysers, steam, and so on. In the with the intrusive magma, we have the magma not penetrating to the surface, but staying in lower levels, but transporting heat close to the surface. So we have also manifestations at the surface, like hot pools, geysers, mud pools, steaming ground, and so on. So we have, of course, also plutons in the area, but the pluton is accompanied by the magmatic active magmatic chamber. So it's different with the two CV2 plutonic places. There's a batholith, so the hot rock, which is not flowing but stable, is the main source of the geothermal energy. But the magma chamber can be associated to those, and there can also be active volcanismus in the area. So in this case, we have also a hot basement, a hot granitic pluton with geothermal anomaly above, with manifestations at the surface, but no active volcanism. Then we come to the extensional domain. So we have this extension, and we have fault planes which have a high permeability, and so we have water flow, hot water, coming up along the fault planes and building in some areas mud pools or hot springs at the surface. So manifestations at the surface for the geothermal anomaly. In other areas there may be no manifestations as a surface, which we call a blind system. And of course here also geophysical methods are very important to find those. So in the case where we have manifestations at the surface, of course there are also other possibilities. So we come to the conduction type. So this is a deep sedimentary basin, maybe separated into smaller sub-basins. But this is an area where we can develop deeper, in normally deeper, maybe 4,000 or 5,000 meters deep geothermal extraction. And we need deep drill holes because the temperature is not so high, but it's still a possibility to develop geothermal systems. So in an organic belt, we have here the subduction and the organic belt, and this picture there are some temperatures and water flow, and we have normally we have a basement which is low permeable, which is mainly petrothermal, and we have sediments with a higher permeability. Now this is the maybe not very often discussed, but from the total potential, the biggest source of geothermal energy is the basement. And here we have temperatures in the basements that allow maybe electricity production or heat use, direct use of the heat. And normally it's covered by a sedimentary cover. And so exploration, of course, here needs special techniques to get some resolution in the granitic or crystalline basement. So we come back to the exploration technologies. I told you before that I will concentrate on geophysical techniques alone, but here you can see, of course, we have different geological methods. We have geochemical methods, which are a great variety and which are very, very important in many geothermal exploration applications. But today we concentrate on the geophysical methods, and I will go through this toolbox of geophysical techniques in the next slides. So here's the same thing again. So in the geophysical techniques, we will talk about gravity, magnetics, magnetotelluric, controlled source electromagnetics, electrical DC resistivity, self-potential, then seismic methods, active seismic methods, passive seismic methods. And as I told you before, normally we add shallow drill holes for heat flow measurements or temperatures also to the geophysical methods. I will not touch today geophysical logging in boreholes, but this is of course also an important geophysical technique. We add raw temperatures from logs, as I told before, from shallow holes, flowing temperatures in hot springs and surface water. We have maps and contours at different depths for the temperatures and cross-section showing temperature. So this all will lead to a conceptual model where we combine all informations which we have from geophysics with geochemistry and geological and other information. So I start with gravity. On the right screen, you can see in the upper part one of the gravity meters. In this case, a quartz-based gravity meters, which is a spring balance, more or less, small but very, very high-tech mechanics. And if we go to the principles of the gravity, if we have maybe a different density in different layers. So here we have a higher density embedded in a lower density environment, and then we have a positive anomaly. So the spring is extended more in the middle because of the heavy material in the valley. In the right side, we have the opposite. In a high density granitic basement, we have a sediment filling with lower densities, so we have a negative anomaly, and of course the spring in the instrument is more attracted from the high density material. So this is how an instrument looks like. It's small instruments, but always mechanical instruments. It takes some time to make a measuring at a certain point. So the gravity is influenced by many factors which have to be taken into account by so-called corrections. So we have corrections for the latitude. Of course, in the pole, the gravity is higher than at the equator, and so we have to correct for the latitude. We have the tides, so we have to know, but of course the tides are very well known. You have it on your computer and you can just subtract it. We have a free air correction. So this is because if the gravity meter is in higher altitude, of course the gravity is smaller, and so you have to correct for this for the altitude of the point where you make the measurements. And then you have in addition, if the measuring point is in higher altitude and the material between the reference level and the measuring point is not filled with air but is filled with materials or with rock, of course this additional rock attracts, and you can correct for a horizontal layer, Bouguer plate, named after Bouguer, to correct for the attraction of this additional plane. So if this plate or the mass between the reference level and the measuring point is not a horizontal plate, but is a complicated structure, complicated terrain, this has to be mapped or taken from a digital elevation model or somewhere, and it has to be corrected. So it's interesting, if you have a mountain close to the measuring point, it makes the gravity value lower. If you have a valley close to the measuring point, it makes also the gravity value lower. So the final result after all these corrections is the Bouguer map, and this is a normally used result of a gravity survey. So here you can see an example where you have the gravity all in a color-coded map. It's a volcanic caldera, and you can see the values in the surrounding and the values in the middle. So here resistivity data are superimposed, which is not part of course, of the gravity measurement. But you can see that the gravity reflects very, very nice the caldera situation. So Every service has a certain output, and you have an output of the fieldwork, an output of the data processing, and an output of the interpretation. So, of course, for the fieldwork, you have the field report, you have to talk about the instruments, you have the first maps showing the stations and all the coordinates, and you, of course, have the raw data of the gravity measurements. From the processing, you have, of course, an extended report, information about the instrument and the software and so used for the corrections. And the final result, as I have shown before, is the Bouquet map and, of course, the process data on a file. Then the interpretation, again, you have a report. You have to bring your interpretation together with the pre-known geological information. You have to write exactly which software was used and which assumptions were made, and you put all this together to a modeling software, and you end up with the interpreted Bouquet maps and profiles, and finally with 2D and 3D images of the interpreted structure. So we come to geomagnetics. So in geomagnetics, everything looks very similar to gravity. So magnetics is also a potential method, so measuring something which is a constant value with only very slow timely variations. So the measured value T, of course, has to be corrected as in the gravity with different corrections. So we have we have diurnal variations because of the magnetic influence of the ionosphere. So the magnetic field is not constant, and so normally this is done by a reference station which is sitting at a fixed point, and you compare always the data coming from the moving station with the reference station. We have altitude corrections as we had in gravity, we have terrain corrections, and we have a normal field. So this is a slowly varying field with distance that is not influenced by local influences, and so this is normally subtracted or corrected by a 2D frequency filter. So this shows again somebody sitting on a reference station which stays here permanently, and another guy is walking around with the magnetometer, or in this way, or it can be mounted on trucks, on helicopters, on planes, or on drones, as in this picture. So the result again is a color-coded map of the magnetic field after all corrections. So you can see here the grid is 50 meters. So this gives a very detailed structure of the shallow, in this case, shallow underground. So again, we have the same things as in the gravity field report: instruments used, coordinates, time and date, important. So we have the raw data and of course the altitudes and everything what you need for the corrections. Then we have a processing as we had in the gravity. We have to describe the processing in detail, the use software, and we end up with data files after all the corrections. The interpretation is very similar, so mainly model-based. So we have to develop models which bring up the same a good coincidence with the method data. We have to add or import information from maybe boreholes and somewhere else, from other geophysical methods, and finally we also end up with 2D or 3D structures. So in the magnetic is also interesting that we have a first and very cheap possibility to make to map one geothermal point. So this is the Curie point, so below in depth greater than the Curie point, the temperatures are higher than the Curie temperature, and we have no magnetism. So if we map this Curie point temperatures, we have a cheap and good information about at least one temperature. So we come to the magnetotellurics, which is in the high entropy areas, the most used geophysical method. Also on the sketch, you can see that we have measuring for the electronic field, and we have coils H, Z, X, Y to measure the magnetic fields. So what is measured is the input from magnetic waves coming from the ionosphere, so natural waves. So here you again, you have the setup, and you make these measurements or can transform it in the frequency domain, and you can see that low frequencies penetrate deeper and high frequencies penetrate only a little. So from a frequency analysis and processing and interpretation, you can develop a resistivity depth model. So here again, the equipment, you can see the coils in this case. You have to put the coils in the X, Y, and Z directions. And you, of course, have a data logger to measure the data. So with the resistivity, you can see the alteration of rock into clay due to the fluid flow of high temperature fluids, and this causes a lower resistivity. So clay has a lower resistivity than the parent rocks. You can also map salinity of fluids. Higher salinity means lower resistivity, and you have dependence of the resistivity of the rock from temperatures, which all could be mapped with MT methods. So here a principal sketch. So you have normally a clay cap. If the hot water and vapor from the reservoir penetrates through the rock, the minerals are altered, and a so-called smectite is built up, which is normally a low resistivity layer which can easily be mapped by those geophysical methods. So this is an example where you can see in red lower resistivity zones which could be clay caps or could show that there is a geothermal anomaly below building hot water and steam to produce these low resistivity parts. Another example and you of course can draw this also in 3D maps in layers in depth, not only at the surface, or in 3D cubes where you can see the lower resistivity anomalies in a 3D sketch. So again, of course, we need all the field information and end up with a data file for the in a regulated format. Then we have a lot of processing because MT is a very difficult method with very specific noise, and it's very hard and needs a long time normally also for data processing and many trials. But we end up with detailed information about the resistivity distribution in the underground. So again, 2D and 3D images are produced finally. So we come to the controlled source electromagnetics. This is the same as before, but with an artificial source, not using the electromagnetic waves coming from the ionosphere, but having our own transmitter. So you have a control about the transmitter, and this makes something easier. This is especially important where the noise situation for MT is bad. The main noise source is industry or cities, and geothermal applications are very often close to cities because we want to use the heat. And in the noise area of the cities, magnetotelluric is very often not applicable, but maybe controlled source is a better choice. So the control source can be made with a frequency domain source, which is normally a big coil, or with a time domain source, which is which are two electrodes, which with a current, DC current, which is switched on and off. So here I have the source, so two electrodes with a current or smaller or larger coils, and the receivers are again, as it was in the magnetotellurics, receivers for the electric field or receivers for the magnetic field. Again, the equipment, not much to be seen, but a very big producer for DC current, which is also a little bit dangerous sometimes in the field, so you have to be careful. We need many kilowatts to have a strong enough source to overcome the noise problems. This is again one of the measurements, so it's called low temp, so it's a long offset, so the distance between the transmitter and receiver was some kilometers, so long offset. But again, you can see anomalies, maybe not so easy to be interpreted in this field case, but it has, in principle, the same output as MT, but is the electromagnetic waves had been produced with an artificial source. We have again, I just go to the right side, you have the same type of information. Of course, it's also a resistivity map, and you can interpret 2D or produce 2D and 3D images of the resistivity distribution, and you can interpret this resistivity values in a conceptual model. Of course, we have also the DC electricity. So the two types before were electromagnetic, so AC. So this is now a DC, which is one of the oldest geophysical techniques. So you have two electrodes and two measuring points, so you can have different geometries to set up the electrodes and the measuring points. You have the current going into the ground, and you have the voltage measured between these 2 points, and then you can produce images like this. So we have a certain model here, and you have the calculated values for this model, and you have the measured values. It's the same area. You can see that many things are very well presented. Other things like this blue part is not visible in the data, so it is not so easy to interpret, and it goes only in a very shallow depth. I will very shortly mention the self-potential so the Earth can also produce its own electricity, like in a battery. So you have different chemical materials, and they can produce a voltage which can be measured. So this is sometimes, but not very often used. So you have no source, but you can measure the voltage between different measuring points. These are normally very low voltages in a millivolt range, and so you need complicated electrodes to avoid artifacts. And it is sometimes used, but not very often in geothermal exploration. This shows an example, the volume change along a line, and the aerial picture, which is a self-potential anomaly, which must have any reasons, of course, to be there. So we come to the seismic methods, active seismic methods, where you have a source for seismic waves, and you have geophones to pick them up at the surface. So they are normally, and that is a reflection seismic method, where they are reflected on layer boundaries and coming back with different travel times. Of course, the deeper reflections need longer to come back, and you pick them up at many geophones, and they are transferred to a recording track. So the layout can be very different. So the classical is a 2D, so the seismic lines. I have two real examples here. So the responsible person at the upper picture wanted to connect boreholes by lines to have an easier interpretation, because he has the validation at the borehole locations. And the other guy on the lower part, so he wanted to have a parallel grid to have something like a 3D result from 2D measurements. So there are enormous different possibilities. So there are still more if you go to in a real 3D. So in this case, you have three possibilities. So you have geophones, red points, and sources, which could be a vibrator. It's the blue points, and this altogether brings a 3D situation. So in the middle, it's has a little bit advantages compared, but it's more complicated in the field. And this zigzags, so here the vibrator can drive continuously on a zigzag line, but this is mainly only used in desert areas. So also in seismic, you have, as in the other methods, a long series of processing of the data. I don't want to go into details. Of course, you on every of those boxes, we should have a separate webinar to talk about it, about static corrections, about normal move out and deep dependent move out, and so on. But I only want to show that it needs a long, very sophisticated chain of processing to come to results like this, which is normally a 3D plot of layer boundaries and of fault planes, which can, of course, today shown in beautiful colored pictures, but also needs interpretation. This is again one of those seismic results. So I don't here want to go into details. So it is the seismic is so established in the oil and gas that everything is standardized. So you have here the standardized formats for the data, and the description of the processing in this has to be described with many parameters step by step, and the end up is a 2D or 3D image of the geological underground, mainly showing the structure. So the seismic is mainly a structural information. So compared to magnetotellurics or the electric methods, which show mainly the fluid filling of the different layers, because the fluid filling defines the resistivity, but the seismic defines mainly the structure, including some maybe in limestone or in carbonates. It can also include the karst information, so facies changes or small things like that. So we come to the passive seismic methods. So in the active methods before, we had a seismic source, and we so-called seismographs, and the geothermal activity in the underground, also the production or the extraction of heat, causes small seismic events, which can be mapped by a network of instruments and located. So here you have the magnitude of the event in the size of the ball, and the color code is a little bit the time. So I think the latest were the red ones, and 1 year before the blue ones, and all the other years before the gray ones. So for interpretation, you need a good velocity model. And so the passive seismic can show you the event locations for local events, the clustering to map fractures, so you can cluster those events along fracture lines, and so you can map the extension of the fractures which are activated maybe by the extraction of geothermal energy. You can have stress estimates, we come to that later. You can do seismic tomography using far events because they travel on the last part of its way to the station through the reservoir, and so you can use tomographic methods to map the velocity field. And the ambient noise, this does not use seismic events, but noise events like ocean waves, and we have interferometric methods to evaluate from those also distribution of the velocities. A special thing is the shear wave splitting. So maybe you have heard of it. It's a shear wave running through a volume with oriented faults in it. So the shear wave is splitting in faster and slower traveling parts. And this delta t, so the time difference between the shear waves swinging parallel to the faults or cross to the faults, this is it gives an information about the faults and the how many faults are there, how big the faults, and so on. There is some information about the faults, which may be also interesting for the estimation of the fluid flow in that volume. So I told you that ground temperature mapping is added to the geophysical exploration by most of the authors. Is considered as a part of the geophysical exploration. So these are normally near surface measurements or shallow drill hole, just temperature measurement. We have here an example with blue low temperatures, red higher temperatures, and you can see here color-coded geothermal anomaly extracted from direct temperature measurements. So if you want to have not only the temperature but the heat flow, you need the temperature log in shallow boreholes. So the heat flow is of course dependent on the conductivity of the rock. But you can interpret all these curves, and you can see here that one borehole is very different from the others. So it needs some interpretation, but it's more or less a direct measurement of the heat flow. I told you before that the stress field is very important for the development of new fractures or the reactivation of old fractures. So the stress field estimates measured, for instance, by borehole breakouts. So the boreholes will normally not stay circular over a longer time, but they will breakouts which are oriented along the field. Tensile fractures observed in a borehole with imaging methods like acoustic imager, and then you have, of course, earthquake resolution, so the so-called beach balls tell you about the orientation of the stress field. And this is a very important input to calculate the reservoir behavior during stimulation or also extraction of geothermal energy. So the last part, I will come back to the geological plays and look a little bit how we can use the different members of our geophysical toolbox for the different plays. And we start with the CV1, so the magmatic plays, and we can see that remote sensing, which is not for me considered as a geophysical heat flow measurements, electrical resistive magnetic gravity, so nearly everything is possible, but of course mainly mainly magnetotelluric and relatives to magnetotelluric are used in this environment. But of course, the others are also needed. You can read here that, of course, it's different. This is extensively used. The self-potential is only used very, very seldom. So this is an example again of a magnetotelluric measurements showing very nicely the hot spots, which are interesting here in the North Island of New Zealand for geothermal applications. Again, a 3D presentation and a 2D, which shows regional that we have very limited, laterally limited, interesting points. So we come to the extension, the CV3. There you have, in general, of course, the surface geology, geochemistry, optional methods, but in geophysics we have gravity, shallow heat flow drilling, MT, and resistive methods, of course, reflection seismic techniques, which is very important for carbon structures to measure the structure of the sediment filling. Airborne magnetics is normally used because it's very cheap and gives some information. Self-potential is very seldom used. We come to the conduction-dominated place. Again, of course, we need structural geology and so on, but we need a lot of seismic because they are not so easily to be catched from with electromagnetic methods. We need sequence stratigraphy, porosity, permeability prediction. We need seismic diagenesis attributes investigation, so cast in carbonates. We need signal attributes for porosity estimates. Of course, MT can be helpful to get some information about the fluids. We can use shear wave splitting in some cases to indicate small fractures in the matrix of the rock. And we need very thorough stress field analysis for geomechanical modeling for the 20, 30 years of production of this field, what will happen to the reservoir after a long time and with temperature changes and so on. So this was it, and I thank you for listening to me. I added my email, so if you have later on questions, you can also write me. Thank you.
Thank you, Horst. That was a very interesting presentation. We have a question from the audience, and it came in about halfway through your presentation. And the question is, why is resistivity apparent in MT methods?
So MT is a method to measure the resistivity. So the frequencies are relatively low, and so the resistivity is not as in radar and high frequency electromagnetics, very different from the DC resistivity. So the resistivity measured with the electromagnetic waves in this low frequency range is very close to the DC resistivity. And the resistivity is an image of the fluid. So the matrix of the rock has very little influence on the resistivity. It's mainly the fluid in the rock pores and if of the salinity, and also the water in the clay crystals contributes to the resistivity. So these are the both targets. So the salinity of the water and the clay content in the rock. And this can be mapped by all electric or electromagnetic methods, including MT.
Thank you. So if any of you have questions, you can either put them in the question and answers box or raise your hand. We have one question, and it's a more general question. They wanted to know what is the most challenging part of imaging geothermal resources?
I think this again depends on the geological play. So worldwide, on the high entropy volcanic areas, of course, the MT is the most used method, and MT is not so easy to interpret. So we made many success in the last years, but we need more dense measurements, and also the 3D modeling software is sometimes not stable, and there can be a lot of artifacts. So I think we have to be very careful with 3D MT interpretations, and it should only be done by experts who have a lot of field experience, because this is really one of the problems. So in other areas, like here in Germany, where we have no volcanoes, and we have deep sedimentary basins, or also carbonates in greater depths of 4 or 5 kilometers. Of course, we look mainly on 3D seismics, and we have to improve the resolution. We look into very small features, so small fault planes, and with a borehole, of course, you can touch such a fault plane, or you can miss it maybe by 10 or 20 meters. So in this case, we would like to stimulate the borehole by hydraulic fracturing, so to make a connection between the borehole and the fault plane, but this is actually not allowed in Germany because of the acceptance problems. But mapping a very small fault planes is here's the main topic. So I think in the worldwide, most interesting is to improve the magnetotelluric, including the noise problems, which I have shortly touched, which is mainly civil or industrial noise.
Okay, great. Thank you. We have another question. So Anthony, please ask your question directly.
Thank you, Horst. That was a very interesting presentation. My question is, how do you usually, when you integrate things like Seismic and MT, reconcile the scale differences or the resolution differences between those two data types? And as an extension to that question, they're actually sensitive, I think, as you pointed out, to very different things, with the Seismic being sensitive more to the structure and the MT being more sensitive to the fluids. And how do you go about reconciling that to develop a coherent picture of what you're trying to image?
So everybody is talking about joint inversion, but as far as I can see, today it's mostly done by hand, so to compare the results of both methods. But you can, of course, always use seismic information, so structural information, as constraints in an MT inversion. So if you fix layer boundaries in an MT inversion, you can have much better results. So the first part of the question was scaling between seismic and... Oh. Hello?
Oh, sorry, my mic's back on. Seismic and MT, I was curious about.
Seismic and MT. So the resolution, of course, is very, very different, because in seismic you have to separate discussion between lateral resolution and vertical resolution, but we are still in a range of about 10 meters, and the MT is of course much less, depending, and of course MT, the resolution is much slower if you go deeper and deeper. So in near the surface it may be better, but in greater depths it is much less. But as I told before, the main way is to import seismic boundaries as constraints into the numerical MT inversions.
Thank you.
Please.
All right. Do we have any other questions for our presenter? Let's see. All right. Looks like we don't have any more questions from the audience. So I guess we'll give them a few seconds to think of some questions, and then let them off the hook, I think. Yep. Everybody is. Oh, wait. There's another question that came in. Alberto, if you'd like to ask your question directly, I have unmuted you. Let's try it a different way. All right. Alberto, please try to ask your question. All right. Well, there may be a microphone challenge there, so I will ask the question.
Yeah.
He says, thank you for your presentation. I'm working in geothermal system, high enthalpy volcanic hosted, whose surface is covered by young lavas. So we can't map the structures using outcrops. What geophysical techniques do you think can be applied both in surface and wellbore geophysics to get a map of the structures in the area? I was thinking seismic profiles and borehole imaging could be good answers.
So I don't know if seismic works well in if there is a lava layer on top, but you have to test it out. But of course, electric methods are applicable in those areas. So we made a lot of measurements in Iceland and also in the Andean South American environment, which good success with all the tricky problems of interpretation, as I told before. But of course, I did not touch in this webinar the borehole possibilities, and inside the boreholes, I agree fully with you that besides the standard techniques, the imaging methods in the boreholes are very important to map the small fractures and the permeability related to those fractures, and there are high temperature tools for acoustic imaging available, going to 200 degrees centigrade, and I think it's very worthwhile to look at the many small fractures you may have in that environment by imaging in boreholes. So try seismic, but concentrate on electric methods and the borehole imaging.
All right, thank you. That was actually, the questions have been very good so far. All right, anybody else who would like to ask a question? Please raise your hand or enter it in the question answer box. All right, I think that we are done with questions, although I think I have one, and it's a very general question. And well, actually, we have another question. What methods would you recommend to survey a dormant volcanic island in a rift setting where the structure is thought to be trachyte shield volcanic center topped with tuffs, hot geysers on the island with ground temperatures over 100 degrees at 50 centimeters depth?
But I did not fully understand. So you are talking about an island with a volcano, and you have high temperatures already in 50 centimeters depth. Is that okay?
Yes, it says where they believe the dormant volcanic island is in a rift setting and has a trachyte shield volcanic center topped with tuffs. And the hot geysers on the island have ground temperatures over 100 degrees at 50 centimeters depth.
So again, the non-geophysical methods are like remote sensing, temperature measurements, measurement of temperatures in surface waters, in mud pools or hot springs or whatever is there, is of course a basis to give you a first impression. And then I would again recommend geoelectric methods like TEM, maybe for these shallow depths. The transient electromagnetic would be an appropriate EM method.
Okay, great. Okay. Thank you.
But be careful if you walk there and the hot temperatures are already in half a meter depth. Maybe it's dangerous.
Okay, great. I have a general question. I'm not from Europe, and I don't know much about geothermal, but I know that there are certain places in Europe that are more successful or prone to be successful in geothermal exploration than others. Outside of Iceland and some of the deeper basins in Germany, what other areas are very pretty active or could be active with respect to geothermal exploration?
Now, this is difficult to answer because, of course, we have the traditional in Tuscany. So in Italy, we had the first geothermal power plant. And so if we go to the high temperatures and to electricity production, the main country now in Europe is Turkey. If you consider Turkey as a part of Europe, maybe not. But Turkey will have more installations than Iceland and Italy in the near future. They are doing a lot for this, and they have a very great potential. But if you don't talk only about electricity production, but also about heating and cooling and direct use, of course, many other countries, including Germany, France. So the whole Paris basin is heated by geothermal. We have applications in Scandinavia. We have a big start of many new projects in Poland. We have in Cornwall some application. So heat productions with temperatures of 70, 80, 90 degrees are possible nearly everywhere. And this refers only to the hydrothermal system, so where you can produce hot water. If you are allowed to frack and to produce heat from hard rock, of course, the applications are nearly everywhere.
Oh, okay. Well, thank you. I appreciate that. Okay, last calls for questions. All right. I think there are no additional questions at this time. So, all right, we'll give them a few seconds. All right. So with that, I'd like to thank you, Dr. Reuter, and thank all of you for attending the SCG Europe Regional Advisory Committee's webinar as part of our webinar series, The State of the Energy Industry in Europe. Please respond to the webinar follow-up email. Let us know what you liked, what could be done better, and suggestions for future webinar topics. Please look forward to our social media posts to register for next month's talk. And I'd like to thank everybody again for attending, and thank you, Horst, for presenting an excellent talk. Thank you very much.
Thank you.
Have a great day.
Bye-bye.
Bye-bye.
Bye-bye.